Have you ever felt that something behaves differently when you look at it? Not in a spooky way, not like ghosts or shadows, but in a subtle, almost playful way, as if reality itself changes when you pay attention. You open the fridge at night. The light is always on when you look, but the moment you try to catch it turning on, it never happens in front of you. You stare, waiting. Nothing. You close the door, open it again. Suddenly the light is on. It feels as if the fridge knows you're watching. We laugh at this idea because in our everyday world, objects don't care about observation. A football doesn't curve differently because the crowd stares at it. The moon doesn't vanish when no one looks at the sky. But in the microscopic world, the world of atoms and electrons, something happens that challenges everything we believe about reality. Particles behave differently when they are observed. Not metaphorically, not philosophically, experimentally. And this leads to a question that sounds absurd, yet sits at the heart of modern physics. Do particles know when you watch them? To understand how scientists arrived at such a strange conclusion, we must travel back more than 200 years, to a time when light itself was a mystery. In 1801, a scientist named Thomas Young performed a deceptively simple experiment. He shined light through two tiny slits, cut into a barrier, and observed the pattern on a screen behind them. If light were made of particles like tiny bullets, the result should have been two bright lines. Instead, the screen displayed a series of bright and dark bands. This pattern, known as interference, proved that light behaves like a wave. Waves can overlap, reinforce each other, and cancel each other out. Particles cannot do that. For more than a century, this seemed settled. Light was a wave. Then the 20th century arrived, and with it came experiments that would shake the foundations of physics. Scientists began performing the same double-slit experiment using electrons. Electrons are particles of matter. They have mass. They carry charge. They should behave like tiny bullets. If you fire tiny bullets through two slits, you expect two lines. But the electrons produced an interference pattern, just like waves. This alone was shocking, but the real shock came when scientists slowed the experiment down and fired electrons one at a time. One electron, not a beam, not a stream, a single electron passing through the slits. Over time, the same wave interference pattern appeared on the screen. Pause and think about that. How can a single particle interfere with itself? Does it split into two? Does it become a wave? Does it somehow pass through both slits at once? These were not philosophical questions. They were experimental facts demanding explanation. By the 1920s, physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger realized that classical physics could not explain these observations. They proposed a radical idea. At the quantum level, particles do not exist in definite states until they are measured. Instead, they exist as a cloud of possibilities, a probability wave. An electron is not simply here or there. It is a range of potential locations. It does not travel along one path. It explores all possible paths simultaneously. Years later, Richard Feynman described this idea in a way that was both shocking and elegant. He suggested that a particle traveling from point A to point B does not take a single path. It takes every possible path, straight paths, zigzags, loops, even wildly improbable routes that wander across the universe and back. Each path contributes to the final outcome. Some reinforce each other, others cancel out. What we observe is the result of this grand interference among possibilities. Now comes the moment where the mystery deepens. Scientists ask a simple question. Which slit does the electron actually pass through? To find out, they placed detectors near the slits to observe the electron's path. And the result was immediate and astonishing. The interference pattern disappeared. Instead of behaving like waves, the electrons behaved like particles, forming two distinct lines. The mere act of observing which slit the electron went through destroyed the wave behavior. It was as if the electron knew it was being watched. But does observation mean awareness? Does the electron sense the detector? Does it respond to human attention? Before we jump to conclusions, we must understand what physicists mean by observation. In physics, observation does not require a human mind. Observation means interaction. To detect an electron, we must interact with it. We might shine light on it, but light carries energy and momentum. When a photon strikes an electron, it changes the electron's motion. At the quantum scale, even the smallest disturbance matters. Imagine trying to measure the exact position of a soap bubble by touching it. The act of measurement destroys what you are trying to observe. Or imagine trying to determine the speed of a delicate toy car by throwing ping-pong balls at it. Each ball changes its motion slightly. The more precisely you try to measure, the more you disturb the system. This is not a limitation of our instruments. It is a fundamental property of nature. Werner Heisenberg formalized this idea in his uncertainty principle, which states that we cannot know both the exact position and exact momentum of a particle at the same time. The more precisely we measure one, the less precisely we know the other. At this point, you might ask, is the disappearance of the wave pattern simply due to disturbance? The answer is deeper. Measurement does more than disturb. It forces the system to choose. Before measurement, the electron exists in a superposition of possibilities. It is not in one place or another. It is in many potential states at once. When we measure, we reduce those possibilities to a single outcome, and that is where the true mystery begins. So if measurement forces a particle to choose a single outcome, what exactly is being lost? Possibility. Before observation, the electron is not a tiny marble rolling through space. It is a spread of probabilities, a range of potential realities. It is not committed to one path. It holds many options at once. When we measure, we remove those options. It is like asking a multiple-choice question and forcing the universe to circle only one answer. But why should nature behave this way? Why should possibilities collapse into a single reality just because an interaction occurred? This question puzzled physicists deeply, and it still does. Erwin Schrödinger illustrated this strange idea using a thought experiment that has become famous around the world. Imagine a cat sealed inside a box with a device triggered by a quantum event. According to quantum mechanics, until the box is opened and observed, the cat exists in a superposition of states, both alive and dead. Schrödinger did not propose this to suggest that cats can be both alive and dead in reality. He intended to show how absurd quantum rules appear when applied to everyday objects. And yet, the mathematics of quantum mechanics insists that superposition is real. So what prevents us from seeing such strange behavior in daily life? Why don't we see chairs existing in multiple positions? Why don't cars pass through walls? Why don't people exist in several locations at once? The answer lies in interaction with the environment. In the microscopic world, particles can remain isolated long enough to maintain superposition. But in the macroscopic world, everything interacts constantly with air molecules, light, heat, vibrations, and countless other influences. These interactions act like continuous measurements. They destroy superposition almost instantly. Physicists call this process decoherence. Decoherence explains why quantum behavior becomes invisible at large scales. The possibilities are still there, but they vanish so quickly that we never notice them. You might now wonder whether observation requires a conscious observer. Does reality collapse only when a human looks? This idea has captured popular imagination, but there is no scientific evidence supporting it. A detector, a photon, or even a dust particle can cause decoherence. Consciousness is not required. What matters is interaction and information transfer. When information about a particle state leaks into the environment, the interference pattern disappears. Reality does not wait for human awareness. It responds to physics. Richard Feynman approached this mystery with humility and humor. He often emphasized that quantum mechanics does not fit our everyday intuition because our intuition evolved in a world of large objects moving slowly. We expect certainty because our senses are tuned to the macroscopic world. But nature at its deepest level operates differently. Feynman proposed that particles explore all possible paths between 2 points, not just the obvious ones, but every conceivable path. Each path contributes a probability amplitude. These amplitudes can reinforce or cancel one another. The paths that reinforce produce the outcomes we observe. The rest fade away through interference. This idea can be illustrated using ripples in a pond. If you drop 2 stones into water, the ripples overlap. In some places, they reinforce each other, creating larger waves. In other places, they cancel out, leaving calm water. The final pattern is the result of interference. Quantum mechanics suggests that reality itself emerges from a similar process. But then we return to the central mystery. Why does observation destroy interference? Because observation eliminates alternatives. When we measure which slit the electron passes through, we remove the possibility that it passed through both. The interference pattern depends on those overlapping possibilities. Remove them, and the wave behavior disappears. It is not that the electron changes its mind. It is that the universe has fewer options available. This distinction is subtle but crucial. The electron does not decide to behave like a particle when watched. The experimental setup determines which possibilities remain. In this sense, reality is not fixed until interactions define it. This idea challenges our classical view of the universe as a machine with predetermined outcomes. Instead, quantum mechanics presents a universe that is fundamentally probabilistic, not uncertain because of ignorance. Uncertain by nature. And yet, despite its strangeness, quantum mechanics is the most accurate theory ever developed. Its predictions match experiments with astonishing precision. It explains the behavior of atoms, the stability of matter, the chemistry of life, and the technology of our modern world. Your smartphone, your computer, your GPS, your medical imaging devices all rely on quantum principles. The strange behavior of particles is not a curiosity. It is the foundation of reality. So we return once more to the question that started this journey. Do particles know when you watch them? No. Particles do not possess awareness. They do not sense human attention. They do not react to curiosity or intent. What changes is the physical situation. Observation introduces interaction. Interaction reduces possibilities. Reduced possibilities change outcomes. The universe is not responding to your thoughts. It is responding to the exchange of energy and information. Every measurement is a physical event. When you shine light on an electron, you alter its state. When a detector records its path, the environment becomes entangled with the particle. This entanglement spreads information outward, making interference impossible. In a profound sense, reality is not a fixed script but a range of potential stories. Observation does not create reality from nothing. It selects one outcome from many possibilities. This idea can feel unsettling. We prefer certainty. We prefer a universe where objects have definite positions and predictable behavior. Quantum mechanics reveals a universe where probability is fundamental. Richard Feynman once remarked that nature is far more imaginative than we are. The fact that particles behave differently when observed does not make the universe less real. It makes it more fascinating. Physicists have proposed many interpretations to explain this behavior. The Copenhagen interpretation suggests that quantum systems do not have definite properties until measured. The many worlds interpretation proposes that all possibilities occur, each in its own branching universe. Pilot wave theory suggests hidden variables guiding particles along definite paths. Each interpretation attempts to answer the same question. What is reality when no one is looking? But perhaps the deeper lesson lies not in the answer, but in the realization that we are part of the system we observe. We are not passive spectators. Every observation is an interaction. Every measurement changes the conditions. Every experiment becomes part of the unfolding story of the universe. When you look at a star, photons enter your eyes, transferring energy. When you touch a surface, electrons repel each other, preventing atoms from passing through. When you measure a particle, you become part of its history. You are not separate from the universe. You are one of the ways the universe observes itself. This realization transforms the question. Instead of asking whether particles know we are watching, we begin to see that watching is itself a physical act, an exchange of energy, information, and influence. The quantum world does not bend to our expectations. It invites us to expand our understanding. It teaches us that certainty is rare, that possibilities are fundamental, and that observation is never neutral. Particles do not know when you watch them, but watching is never passive. Observation changes conditions. Conditions change outcomes. Outcomes shape reality. And in that subtle chain of cause and effect, the universe reveals something profound. Reality is not a single path, but a tapestry woven from possibilities, interactions, and choices. The next time you hear someone say that particles know when you watch them, remember the deeper story. It is not awareness, but interaction. Not consciousness, but physics. Not magic, but measurement. And yet, there is poetry in the realization that by observing the universe, we become part of its unfolding. We are not outsiders looking in. We are participants. And perhaps that is far more astonishing than the idea that particles know we are watching.